Hey everybody, it's Miss Berry. In this video, we are going to go over section 8.1, and this is where we're starting confidence intervals. So you will need your calculator, so go ahead and pause the video if you need a second to find that, and then I'm going to share my screen and we'll get started. All right. There we go. So now hopefully you can all see my screen. So chapter 8 is all about confidence intervals, and we're also going to learn about a new distribution called the t-distribution. That's in section 8.2, so in the next section. But today we are starting with something that is very easy to do in the calculator. The idea, the concept behind what we're doing is a little bit more complicated, but the execution of the concept is very simple and straightforward. All right, so chapter 8 is all about confidence intervals. This first section, we are estimating population means. All right, so we're estimating population means where the population standard deviation is known. All right, so that is the general idea here, is that we are trying to provide estimates for a mean when we know we have some background knowledge about this variable and we already know the population standard deviation. All right, so in this chapter, we're moving into the inferential statistics portion of the semester. So if you recall from the beginning of this semester, inferential statistics is where we use those sample statistics. So we're using those sample statistics, those descriptive statistics that we calculate, the sample mean, standard deviation, variance, range, median, all those things, as well as those graphs that we learned how to generate. To provide estimates for population parameters. And what's powering inferential statistics is probability. So we have all of those probability concepts being used in the background of our calculator, and that's what's powering these inferential statistics that we're going to be working on. All right, so a couple of definitions here. A point estimate, that's what we've been doing. We've been calculating point estimates like the sample mean, right? So an example of a point estimate would be the sample mean. Example of a point estimate is the sample mean. All right, so a point estimate is just where you use a single number to estimate a population parameter. So we are using the sample mean to estimate the population mean. Now, what's even better and more powerful than a point estimate is what we call an interval estimate. So this is where you're just given a range of possible values for a population parameter. So instead of saying, okay, our average, the average temperature in Brunswick is 85 degrees. An interval estimate would give you a range of values. So you might say the average temperature in Brunswick is somewhere between 70 degrees and 100 degrees. All right, so you're giving a range of possible values for that population parameter. And so that can be even more powerful than a point estimate. So using a range of values rather than just a single number to estimate a parameter. All right, and so the way that we calculate these interval estimates is through what we call confidence intervals. All right, so we're going to be calculating an interval estimate by computing a confidence interval. And in order to generate a confidence interval, we have to choose the level of confidence. Now, how do you choose that? Well, it usually depends on what field that you're doing research in. So different fields they have different standards for their level of confidence. But the general idea here is that the larger your confidence level, the wider your range. All right, so let's write that down. So the larger, or we'll say the higher your confidence level, the wider your range. right? So if you want to be really confident, if you want your estimate to be, your interval estimate to be really high, if you want to do like a 99% confidence interval or a 98% confidence interval, what's going to happen is that that range of numbers is going to get wider and wider. So instead of being, say, like 70 degrees to 100 degrees for our, estimate of the temperature in Brunswick, it might go up to like 50 degrees to 110 degrees. So that interval estimate is going to get wider and wider as you increase the confidence level. All right, so the sort of complicated part of confidence intervals is the concept or the interpretation behind the confidence interval. All right, so let's read through this. It says the level of confidence is called C. All right, so that'll be something that we have to plug into the calculator. So you'll need to know that C represents the confidence level. And in our calculator, C, they want a decimal version for C. All right, so they want you to put C in its decimal form. So if it's 90%, if it's a 90% confidence interval, C would be 0.90. All right, so in your calculator, they always want C to be in its decimal form, not in its percentage form. All right, so here's the interpretation of the level of confidence. It says C is the percentage of all possible samples that will produce interval estimates that actually contain the population parameter. All right, so if we said that we were using a 90% level of confidence, we would expect 9 out of 10 confidence intervals produced to contain the true population mean. So 9 out of 10 corresponds to 90%. If you chose something like a 98% level of confidence, you would just bump that up and say like 98 out of 100 confidence intervals would contain the true population mean. All right, so our confidence, that should say a confidence interval. The typo. A confidence interval. A confidence interval is just an interval estimate that is associated with that previous level of confidence that we talked about. Okay, so when we are interpreting confidence intervals, there's a general sort of template that we can use for interpreting confidence intervals. So we usually say something like, we are blank percent confident. You would just fill in the blank with whatever your confidence level was. We are blank percent confident that the true mean blank. So that's where you would describe the variable. So you would just give some description of your variable, that the true mean blank is between, and then you would fill in your numbers. All right, so the numbers are going to come from when we calculate the confidence interval. Those two numbers are going to be like the lower end of your confidence interval and the upper end of your confidence interval. Okay, so pause the screen and write that down, or excuse me, pause the video and write that down if you need to. That's something that I would put on my little formula sheet. That's something that if you go on and take another stats class, it's going to be important that you know how to interpret that. I think that really the interpretation is sort of the most important thing that you can get here. Every program that you use, whether it's, SPSS or Excel or the calculator or R, whatever kind of statistical program you're using, the way that you calculate the confidence interval is going to be different. You always might have to end up Googling something about like, how do I calculate confidence interval in SPSS or in Excel? But the interpretation is going to remain the same. So it's always going to be, we are, say, 90% confident that the true mean temperature of Brunswick, Georgia is between blank and blank. All right, so that interpretation is going to remain the same no matter what program you're using. All right, so here is some height data that I calculated from the students in my class one semester. It says use the height data below to answer questions A through C. Assume that the population standard deviation is 4.26. This is going to be important moving forward. So when you see this wording in the problem, you know that you're going to be doing what we call a Z interval. All right, so if sigma is known, you use what we call a Z interval. Remember, Z stands for the standard normal distribution. All right, so we are calculating this confidence interval using the standard normal distribution. All right, so anytime you see that wording, when you see the words population standard deviation is blank, then that means you're going to do a Z interval. All right, so here's our data. The first thing that we're asked is to provide a point estimate. And for this section, the point estimate is always going to be the sample mean. So let's grab our calculators. Okay, right, mine should be coming up in just a second. Here we go. All right, so there's my calculator. If you have something in your screen, go ahead and clear it out. Always nice to start with a clear screen or a blank screen. All right, so to get to the confidence interval screen, you're going to hit the stat button. And actually, we can't even do the confidence interval yet because we have to type the data into our calculator. So that'll be the first thing we do. But if you go over to test and you scroll down a little bit, you see that Z interval option. All right, so that's where we're going to be going after we get the data typed in our calculator. All right, so let's go back up here, go over to edit. All right, so if you're starting from your blank screen, you're just going to hit the stat button and then hit edit and clear out anything you've got in there. You can see I've got a little table in here. Okay, so now I'm going to start typing my data in. I'm typing everything into, I'm typing all of these numbers into L1. Okay, so I'm typing everything into L1. Let's see if I can get both of them on the screen at one time. Okay, cool. All right, 63, 64, 67, 73. If you need to pause the video and type yours in, that's fine. All right, and then, oops, always go back through and make sure you typed everything in correctly. That's what I'm doing now. Okay. So far, so good. All right, everything looks good. So once I've got my data in my L1 column, I'm going to go back to stat, and this time I'm going over to test. So go over to test, and then we're going to scroll down to Z interval, hit enter. And you're going to tell it that you're using a data set that's typed into the calculator. And so you can see I just went over to data and I hit enter. And then I'm just scrolling down. See how it's saying L1? So that's going to be where you tell the calculator, hey, this is the column that I typed the data into. So that's already correct. Now I need to put in what my population standard deviation was. I said that was 4.26. That was given to us in the problem. And then we will go down here and hit calculate. Let's see. We're supposed to be doing a 95% confidence interval. That's part B. So we'll go ahead and type in 0.95. Right, and then we'll go down to calculate and hit enter. And see how it put the sample mean in there for us. So we'll go ahead and write that down. The sample mean was 65.75. Right, so 65.75. Let's write that down. X bar, that's our point estimate, is 65.75 inches. All right, so we're saying on average, students were about 65.75 inches tall. So that's about 5 3/4. So 60 inches is 5 foot. So that would be 5 3/4. All right, and now we can construct the 95% confidence interval, or I should say report the interval since we've already constructed it. All right, so there's our interval, and we're supposed to be doing one decimal place. So we'll do 63.9 to 67.6. 63.9 to 67.6. Okay. 63.9. Naturally, I've already forgot. 67.6. And I just always put little parentheses around that just to indicate that these numbers go together and that they are our interval. So the lower end of our interval would be 63.9 inches. So that's about almost 5'4", right? So that'd be 5'3" and 9/10 of an inch, all the way to 5'7" and 6/10 of an inch. All right, so let's interpret that confidence interval. All right, so we would say we are 95% confident because we were doing a 95% confidence interval. We are 95% confident that the true mean height of Miss Berry's stat students and you can see again, I'm just following that template that we talked about earlier. All right, so we are 95% confident that the true mean height of Miss Berry's stat students is between 63.9 inches and what do we say, 67.6 inches? I think that was right. Yep. All right, so what this means is that if we were to generate 100 confidence intervals, 95 of them would contain the true population mean for the height. All right, so we're 95% confident that the true mean height is between these two numbers. Of course, there's always a chance that, the true mean lies outside of those numbers, but we have sort of mitigated that chance by using this very high confidence level. You could even do confidence intervals that were even lower than this. You could do an 80% confidence interval. You could do a 60% confidence interval. All right, but in general, we see things like 80, 85, 90, 95, 98, and 99. So in real research. Okay, here we're looking at a problem that came straight from the homework. So it says, the Water Works Commission needs to know the mean household usage of water by the residents of a small town in gallons per day. Assume that the population standard deviation is 2.4 gallons. So that's pretty small, right? So this is saying that on average, the population standard deviation for gallons of water used per day is about 2.4. And it says the mean water usage per family was found to be about 15.8 gallons per day for a sample of 4,331 families. Very large sample. Construct a 99% confidence interval for the mean usage of water. Round your answers to one decimal place. All right, so we get a bunch of information here. We've got that the population standard deviation sigma is 2.4. We've got that our sample mean, right, so it says mean right there. It says sample right there. So putting those together, I know that's the sample mean is 15.8. My sample size is 4,331. And I'm supposed to be doing a 99% confidence interval. So I'm going to write all of that stuff down. I think that's a great way to just kind of guide your thinking whenever you're doing these problems. If you come back and look at them later, you'll be easily be able to figure out exactly what you were thinking. All right, so sigma, the population standard deviation was 2.4, X bar, the sample mean, they told us was 15.8. We didn't have to calculate it. The sample size was 4331. And then my confidence level, remember in decimal form, that would be 0.99. All right, 0.99. Okay. Let's grab our calculator. I'm going to write all this stuff down so I don't forget this time. Use 0.99. Okay. All right, let's grab our calculator. Clear this all out. I'm going to clear out my stuff at the bottom. All right, so we're going to go to stat. We don't have any data to type in this time, so we're just going to go straight over to test, go down to Z interval, hit enter. And this time you're saying, okay, I don't have a data set typed in, so I'm going to go over to stats, hit enter. So you only go to data when you are manually typing in everything into L1. All right, so population standard deviation, they told us that was 2.4. The sample mean, they told us was 15.8. 15.8. Sample size was very large. It was 4331. And then confidence level was 0.99. All right, so go down to calculate. And I think you'll notice that this interval is much wider. So last time we went from 63 inches to 67 inches. So that was only 4 inches that confidence interval spanned. I think you'll find that this one spans an even larger range of numbers. All right, so I'm going to hit enter. And there's my confidence interval. All right, so 15.7, they said to do one decimal place. So 15.7 to 15.8. Wow, this is a small range, right? And I guess that's because our population standard deviation was so small. All right, so let's jump back over to our presentation. We're rounding this to one decimal place, so that's 15.7 to 15.9. All right, so I thought we were going to see a larger interval, but we actually ended up seeing a smaller one because we had that very small population standard deviation. All right, so 15.7 to 15.9. And then we will write a sentence. You don't have to write a sentence interpreting it, but like I said, that's really the part that will stay consistent no matter what stats class you take is the interpretation. So you may, if you go into another stats class, you might use a different program. You might use R, you might use SPSS or Excel, but the interpretation will remain the same. All right, so we would say something like, we are 99% confident that the true mean, and this time our variable is, let's see, mean household usage of water. All right, so that the true mean household usage of water, and again, you can usually get the variable, the description of the variable just by reading the problem and copying down their wording. All right, so we're 99% confident that the true mean household usage of water is between our two numbers, 15.7 gallons and 15.9 gallons. And I guess we could say per day. That's a little bit more specific and gives you a little bit more information. Okay. All right. Hopefully y'all are getting the hang of this. I think calculating the confidence interval is one of the easiest things we do in this class. It's just that if you spend some time thinking about the interpretation of the confidence intervals, they can get complicated very quickly. All right, so let's look at this third one, and I'm going to ask you, after we read through the problem together, I'm going to ask you to pause the video and try this one on your own and make sure we get the same numbers. It says, a toy manufacturer wants to know how many new toys children buy each year. A sample of 1,029 children was taken to study their purchasing habits. Construct a 95% confidence interval for the mean number of toys purchased per year if the sample mean was found to be 6.9. Assume that the population standard deviation is 1.9. Round your answers to 1 decimal place. All right, so a few important things here. There's our sample size, there's our confidence level, our sample mean, and our population standard deviation. So I see that word population standard deviation. I'm thinking, okay, I'm doing a Z interval. You're going to see later on in like 8.3, section 8.3, where if we don't know the population standard deviation, then you have to use a different type of interval. So that's why I'm just trying to emphasize that now. All right, so take a second, pause the video, and come up with your confidence interval, and then unpause it and make sure you get the same answer as me. All right, so I'm just going to do this in the calculator quickly without really talking. All right, 6.8 to 7.0. 6.8 to 7.0. All right. All right, so if we were interpreting this, we would say something like, we are, this time it's 95% confident that the true mean, let's see our variable here, number of toys purchased per year, that the true mean number of toys purchased per year. And I'm just going to put in there for children, I guess, or by children, whichever one you wanted to say, is between 6.8 toys and 7 toys. Okay. And of course you could word this. I'm not an English teacher, so I'm sure there's a way that you could word this so that it flowed a little bit better. Like you might want to say we're 95% confident that the true mean number of toys purchased for children is between 6.8 toys and 7 toys per year. So you might want to like shift that per year to the end if you were really writing this in a research paper. I'm sure you could make this flow better. Oh, and I also wanted to say, so sorry about my very sloppy handwriting. Sorry about that. All right. Hopefully y'all got the same confidence interval. Hopefully this is all coming together for you. The last thing we're going to do in this section is another very powerful tool. This is if you knew that you wanted to say, if you were kind of working backwards, you're like, okay, I know that people in my field, maybe your field is marine biology. I know that people in my field use a 95% confidence interval or a 95% confidence level. What do I need my sample size to be so that I can get to that confidence level without having a super wide interval? All right, so this formula tells you the minimum sample size. So what's the smallest number of people or animals or whatever that you would need to sample to estimate the population mean to this level of confidence? Okay, so there's a lot of pieces here. N, of course, we know is the sample size. N is equal to this big fraction all being squared. Here we have this really weird symbol that you've never seen before. It's called Z sub alpha over 2. Z sub alpha over 2. So I'll write that down. This is called a critical value. So if you were reading this out loud, you would say Z sub alpha over 2. So Z with the subscript alpha over 2. All right, so this is called a critical value. We're going to be calculating critical values all through this section, or this chapter, I mean. All right, so Critical values are associated with a particular level of confidence, and this is again specifically for scenarios where you know the population standard deviation. If you don't know the population standard deviation, you have a whole other set of critical values. All right, so these are our critical values for the standard normal distribution. All right, and it says that if you wanted to get to a 99% confidence level, this is your critical value. For a 98% confidence level, this is your critical value. All right, so this first piece is just the critical value multiplied by this population standard deviation, which will be given to you in the problem. Again, the only thing that will be not given to you in the problem is the critical value, and that's given to you right here in this table. All right, so critical value given to you in the table times the population standard deviation given to you in the problem divided by what we call the margin of error. Now, this is another thing that's sort of standard to different fields. So different fields have different margins of error that they traditionally use. And so you would read other papers from similar people, similar researchers in your field to figure out what that margin of error would be. But that'll also be given to you in the problem. All right. Make sure if you're taking notes, make sure you write this table down because we're going to have to reference it in just a second. All right, so make sure you write that table down. All right. Whoops, wrong way. Okay, here's our next problem. It says the electric cooperative needs to know the mean household usage of electricity by its non-commercial users, so that would be like residential customers, in kilowatt hours per day. kWh is kilowatt hours. They would like the estimate to have a maximum error of 0.09 kilowatt hours. A previous study found that for an average family, the variance is 1.96 kilowatt hours, and the mean is 17.6 kilowatt hours per day. If they're using an 80% level of confidence, how large of a sample would they need to estimate the mean usage of electricity? Now, you're going to see this in every problem where you're estimating the minimum sample size. They always want you to round your answer up to the next integer. And that's because we're talking about people or objects or animals here. So you can't sample like 101.7 turtles. All right, so you're saying, okay, well, this is 7/10 of a turtle, so let's just go ahead and round this up to 102 turtles. All right, and they want you to totally ignore, sorry about that. They want you to totally ignore your standard rounding rules here. So even if you got like 101.3, they're saying, okay, that still represents 3/10 of a turtle that we need to sample. So let's go ahead and say we're going to sample 102 turtles. All right, so in this case, it's people because we're talking about people that use electricity. But if you were doing this for like marine biology or whatever, it doesn't have to be people. It can be animals. It can be shells. It could be, anything, bugs. All right, so we're always rounding that answer up no matter what. So we're ignoring rounding rules. Okay, so here's our formula. Sample size equals critical value times population standard deviation divided by the margin of error, all squared. And here's our little table with our critical values. All right, so I told you in the problem that my maximum error or my desired margin of error was 0.09. I told you that the variance was 1.96 and that the mean was 17.6 and that we wanted to use an 80% level of confidence. All right, so 80% level of confidence, that's the bottom row of the table, that's 1.28. Now, I want to say, if I remember correctly, that your homework sometimes will put 85 on there. And if you need to find the 85% critical value, you can just Google that. Just Google like 85% confidence, or excuse me, 85% critical value normal distribution. Or you can click the tutor button. You could probably find it there too. All right, so we do have to do a little bit of work before we can use the formula because they gave us the variance instead of the standard deviation. All right, so let's go ahead and find the standard deviation. All right, the standard deviation, as we know, is the square root of the variance. So take the square root of 1.96 to get the standard deviation. All right, so they told us that the variance was 1.96. All right, so the square root of 1.96 is 1.4. All right, now we can go ahead and plug everything in. So n is equal to critical value times standard deviation over margin of error. So parentheses, critical value times standard deviation over margin of error. Close that parentheses, raise it to the second power. All right, let me show you how you would plug that in. Whoops, there we go. Clear that out. This is how I plug it in. I do 1.28 times 1.4 over 0.09 and then squared. So I'm not doing anything fancy. The only time I use parentheses is just to put it around the first part of the fraction and around the end of the fraction. And there's our answer, 396.45. We ignore our rounding rules and we always round this up to the next whole number. So that'd be 397 people that we need to sample. All right, so let me see if I can find the right screen. There we go. 397 people. We'll say people or customers or whatever. Right. So you would go back to the electric cooperative and you would say, okay, based on the previous studies that y'all have done, where y'all found the variance, and based on the level of confidence that you're wanting and the margin of error, you need to sample 397 of your customers. All right, and here's our last question. It says, a research scientist wants to know how many times per month a certain strand of bacteria reproduces. He wants to construct a 90% confidence interval with a maximum error of 0.21 reproductions per hour. Assuming that the mean is 10 reproductions and the variance is known to be 6.25 reproductions, what's the minimum sample size required for the estimate? All right, and so again, we see these directions, round your answer up to the next integer. All right, so there's our formula, our table. Now let's read through the problem. All right, 90% confidence level. All right, so that means our critical value is going to be 1.645. All right, 90% confidence level, 1.645 is our critical value. We've got a maximum error or our margin of error is 0.21, so that's E. And then I've got our sample mean as 10, and then once again, they gave us the variance instead of the standard deviation. So let's start by finding the standard deviation. I know it's the square root of the variance, so square root of 6.25, and that is 2.5. So if you want to verify that, you can pause the video and check it on your calculator. Right now, I'm just plugging in everything into my formula. There's my critical value. All right, so sample size equals, big parentheses, critical value times standard deviation. So critical value, 1.645 times standard deviation, 2.5, over our margin of error, 0.21, close parentheses and square. All right, now I want you to practice plugging that in. So pause the video, practice plugging it in, and you should get 384. All right, so once you round up to the next integer, you should get 384. So you would, if you were working with this research scientist, you would say, okay, you need to sample 384 strands of bacteria. Okay. All right. That is, let me see if I can get back on the screen here, if you can find me. There I am. Okay. So that is everything for this video. If you have any questions, please let me know, and I'll see y'all in the next one.